Okay. Hello, everyone. Today we will begin to study Chapter 6, the transport layer. But before beginning the new chapter, we will continue to review some questions. And last time we have finished the comprehensive application questions. Now review some questions. Question 1. IP protocol provides A, B, C, or D. C, right? Unreliable and connectionless. The PIN uses ICMP protocol to detect if host is reachable or not. And the checksum field in IP head is used to check in only IP head portion. C. The total number of condition field is 3. The total number of broadcast field is 2, because this router make the whole network into 2 broadcast portion. Then 5 is a small calculation questions. Is a small questions. How to solve this kind of questions? A host has an IP address 172.16.7.131/26. /26, that means it's that we know the network mask, and we know the length of the prefix. So the broadcast address of the subnet on which the host is located is. This is very basically questions. So from the 26, we know the boundary between the boundary between the prefix and the host portion located at the fourth byte, right? So we should turn the fourth byte, that is 131, into decimal notation, into the binary notation, right? So (131) into binary notation, it is 128 plus 3 that is 1. And we know the boundary, and we know from /26 that the boundary located here, there is 2 bits. So the boundary locates here. Then we know the broadcast address of this subnet, that is turn the last 6 bits into all 1. So we get the last byte is 10 10, then followed 6 ones, right? So 10 1111 10, then 1111, that is 191, right? So the answer is B. Answer is B. So these kind of questions, how to solve that, we should grasp the method. From the /26, we determine the boundary between the prefix and the host portion. Then know the boundary located where, which place, located at the 4th place, right? Because this is 8 bits, 8 bits, 8 bits, the last 8 bits. The total in bits is 32 bits. So they located the 4th. Then, since the boundary located at the 4th byte, so we only need to turn the last byte 131 to the binary notation. Here 10000111, right? So then the broadcast address should make the host portion to the all 1, and the other bits keep itself. So we get 10111111. That is then turn to the binary notation, then to the binary notation to the decimal notation. We can get the answer B, right? So although this is a small calculation, but it is some complex, because we should determine the boundary, then turn the decimal notation to the binary notation, then to the binary, turn the binary notation to the decimal notation. Okay, that is, so I hope everybody understand how to solve this kind of questions, like question 5. Question 7, it is similar to the question 5. Just now we know /26, but now it directly to us the subnet mask, right? Directly to us the subnet mask. Then the host with IP address 192.55.12.116. Then question is, what is the host number portion is? So we should start from the subnet mask. Since 2555 means all 1 bits, all bits is 1, right? All bits is set with 1. Then we should know, we should determine what kind of binary notation. The 240 is 240 means 240. How to turn to the binary notation? We can use this non-division method. For example, you can divide by 16 sorry. Then here is a 1. Here is a 1, right? Here's a 1. 16, 8, remain 8, 80. So here is a 5. That is, we determined the 240's binary notation is 1, 1, 1. How many 1 bits? 4 ones. So 240's binary notation is 1, 1, 1, 1. Then follow the 4 zeros. That is, so the binary between the prefix and the host portion locates here, right? All 1 means the prefix. All 0 means the host portion. So we should determine 116's binary notation, right? Binary notation. What's the 116 binary notation? We can divide 16, right? 7, 1, 1, 2, right? Then 4. That is 116 binary notation is 0 followed 4 or 3 ones, then followed with 0, 1, 0, 0, right? So this is 7 here. This is 7. This is 4 here, right? So the last 4 bits, actually is 0, 1, 0, 0. So from the 0, 1, 0, 0, we know the answer is A, 4. Or you can directly from the remaining 4 to get the host portion, right? So this is then we will review. Then we will review the short answer questions. Please briefly describe at least the 3 solutions to the IPv4 address shortage. Then we know we can use the first solution is subnetting, subnetting. The second solution is classless interdomain routing, CIDR. The third solution is we can use a private address. We can use a private address combined with network address transmission, NAT, right? Then the fourth solution is the ultimate solution. Ultimate solution is using the next generation of IP. The next generation of IP provides a very huge number of IP address space. So we can use IPv6. So we can at least list at least the 4 solutions: subnetting, CIDR, private address combined with network address transmission. Then the last one is IPv6, the new generation, and because it provides this number of IP address. This is the short answer questions. Probably we have other short answer questions. This is just an example. Just the example. Okay, then we continue to illustrate how to calculate the Wireshark and analysis questions. An IP packet is captured with Wireshark, just as the experiment, what we have done in experiment 1. It is shown in the figure here, 45000279, etc. From the information captured with Wireshark, we can determine the value of each field of the IP packet. For example, the header length. And for example, the header length and the total length of the IP packet, and the protocol field, and its meaning. And what is the source IP address and destination IP address? And the TTL checksum field, and what's the source port and destination port? What application protocol does it mean? So from the information captured, we can determine each field value and its meaning. So at first, the basic method is to filling the information into each field of the IP packet, since we can have appendix in the final assignment or examination. And so 4500 4500 this is a hexadecimal. This is a hexadecimal notation. So each character occupies 4 bits. Each character occupies 4 bits. 2 characters occupies 8 bits. So we filled into each blank of the IP packet and we can determine the value of each field of IP packet. So when we finish filling the values, we can determine the meaning, right? Determine the value and its meaning. So for example, write out the header length. The header length here with 5 field here. So in bytes, we should times 4 because the value divided by 4 then filled here. So the actual header length in bytes is 20. That is 5 times 4. 5 times 4. Then 00 is a type of service. The total length is 279. The total length is 279. We should turn to the decimal notation. 2 times 16 squared plus 7 times 16 plus 9. So that is, we can get the value. We can get the value is 633 bytes. 633 bytes, right? So then the protocol field is 6, right? 6. So from we can look up the port number table. The port number table, 6 means TCP encapsulating IP packet. So it means the payload encapsulate TCP segment, right? That is okay. 3. What is the source IP address and destination address? So the source address is 0A, 0A, 01, then 5F. We can turn to the dotted decimal notation. Is source IP address is 10.10.1.95. With the same method, we can determine the decimal notation of destination address. That is 218.30.115.123. Then TTL here. TTL is 80 in hexadecimal. That is with decimal notation is 128, right? 80 in hexadecimal actually in decimal actually is 128 in decimal notation. Then checksum field is 0. This is 0. The source port, since from the protocol number is 6. 6 means TCP. That is in the data encapsulated TCP. But here, whether or not there is an optional field, we should determine from the value of header length. Here is 5 means the length of the header is 20 bytes. That means no optional field, right? So after 737B, that is 0738. should fill into the header of the TCP segment from source port 0738 and then 0050 filled into the destination port, right? So the source port is 738 0738 in hexadecimal notation equals 1848 in decimal notation. And then destination port is 50 in hexadecimal notation equals 80 in decimal notation. So that 80 is less than 1024, so it is a well-known port number. A well-known port number has a special meaning. So we should look up the port number table here. 80 means the application protocol is HTTP protocol. Here 7, right? Here 7. Here 80 means application protocol uses HTTP. So application layer protocol is HTTP because HTTP uses the well-known port number 80. Do you understand? Then we continue to illustrate how to calculate the subnetting scams. Subnetting is typical and is simple questions, but how to solve subnetting scams? I will give you an example. So question A is for subnetting. Question 5 is for CIDR scams. So we give 2 examples, each one for subnetting, and then other is for CIDR. Then a network address block is 172.18.00 will be divided into 1000 subnets. Then we should determine some values. What is the subnet mask? What is the minimum address, maximum address, and broadcast address of the first subnet with the minimum subnet number? Then minimum address, maximum address, and the broadcast address of the first subnet with the minimum subnet number. Notice that subnet and the host portion for host cannot be all 0 or all 1 bits. How to determine these values? Then I will illustrate how to solve this kind of questions. Then subnet, we know subnet scams is based on classed address. So we should determine from the 172 to determine which class is this network address. So 172 plus. We should divide it into binary notation. Okay, so 16 0. That is 172 is 1010. It is 10. It is 10, right? It is 10. 1010. Then followed 1100 is 12, right? Is 12, right? So we can get the first 2 bits is 10, right? 10. Since the beginning 2 bits is 10, what class is this network address? It is B, right? It is a B class. It is a B class. Is 10. 0 is A. 10 is B class. 110 is a C class, right? So it's a B. B means IP address has 4 bytes. Right? Has 4 bytes. So B class, then the first 2 bytes for network portion, then the other 2 bytes for host portion, right? So from we turned the decimal notation to the binary notation, we can determine the first 2 bits is 10. From the 10, we determine the class of B. From the B, we can determine the binary notation between the network portion and the host portion, right? So now we know the binary is here. 2 byte network portion, 2 byte host portion. Then subnetting is borrowed some bits from the host portion. We borrowed X bits from the host portion. Okay? We assumed that we borrowed X bits from the host portion. Then what is the value of X? So X squared of 2 should greater than or equal to the 1000. 1000. Okay? 1000. Then we get the minimum value which is satisfied this inequation. So we can get X equals 10. That means we can borrow 10 bits from the host portion. This is 8 portion. So here, 2 other 2 bits is borrowed 2. So then the minimum, then what is the subnet mask? Subnet mask is network portion. Network and the subnet portion should set all 1. Should set all 1. So all 1 is we can write with or 1 we can write with the subnet mask is the first 3 bytes is all 1. We write 255.255, right? Dot 255 dot the last byte in binary notation should be 1 1, then followed with 4 followed with how many bits, how many zeros? 6 zeros, right? 6 zeros, right? So that is 128 plus 64. That is 192. 192. So the subnet mask is 255.255.255.192. That is the first result, subnet mask. Okay, do you understand? Do you understand? Then, for the first subnet, so we should determine the first subnet with the minimum subnet number. With the subnet this number. So now we have no blackboard, so it is some difficult for me to write with mouse. Now 4 bytes, right? 4 bytes. The first, then the binary locates here, right? 2 bits. Then the network address is 172, right? 18, 0. This byte is 0. Then the first, the minimum subnet number, is 0, 0, 0, 0, 8 zeros, right? 8 zeros, then 0, 1. 0, 1, right? Then this is this bits 0, 1. Since notice that the subnet and the host portion cannot be all zeros or all 1, right? So the minimum subnet number here, 2 bits, is set with 0, 1. Then the other 6 bits should set the minimum address. Minimum address should set from 1, not 0, right? Not 0. 6 bits. So the minimum address is here, right? So now this is 64. This is 1. 64 plus 1 is the minimum address. is 65, right? This is a 64. This is a 1. 64 plus 1 is 65. Then we get minimum address. The maximum address then should be 0, 1, then 1, 1, 1, 1, 5, 1, then followed 0. So this binary notation is 128. 128. We can get the maximum address. Right? So then what is the broadcast address? Broadcast address that is 0, 1, 0, 1, then with 6 ones, right? So the broadcast is dot 127. Do you understand? 127, right? Do you understand? Okay, let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Okay, let's continue. So just now, we illustrate how to solve this kind of question, like question 4 about subnetting. Now, I will illustrate another kind of questions, CIDR. So, a block of IP addresses. Is 194.24.0.0/19 is available. Suppose that we assumed that 3 universities applied address from this IP address block. Cambridge University is about 2,000 addresses. Edinburgh University is asking for 1,000 addresses, and Oxford University asks for 4,000 addresses. Then, if you are an address manager, if you are an address or system ISP manager, how can you assign the addresses with CIDR schemes for these 3 universities? Please assign addresses. For these universities with CIDR. So I have listed the results, but how to solve? So I will illustrate. Then the address block /19 starts at the base address, right? The base address 194.24.0.0/19. What is the meaning of the 19? 19 means the length of the prefix. So the length of the host portion. Is the length of the host portion. The length of the host portion should be 32 minus 19. Right? 13. The length of the host portion is 13. So, since the length of the host portion is 13, so the number of the IP addresses of this block is 13th squared of 13th power of 2, right? It is 8,192. Do you understand? So then the total number of IP address is 8,000. 192. Then the address block can be described with binary notation as we extend with binary notation as with red bits 11000010 0011000000. Then followed with 13x. X, what is the X meaning? X means the bits can be 0 or 1. So that is X means these bits can be from all 0 to all 1, right? All 0 to all 1, because X means it can be 0 or 1. So we assign addresses for the first university. Then the Cambridge University needs 2,000. The Cambridge University needs 2,000 addresses. So from the 2,000 addresses, we can determine the length of the host portion for Cambridge University, right? For Cambridge University. So x to the power of 2 should larger than or equal 2,000. We can determine x with the minimum value 11, with 11, right? With 11. So the length of the host portion has 11 bits. 11 bits can be from all 0 to all 1, denoted by XXX, 11x bits, right? So then the original address block has 19 fixed bits. Do you understand? So since the original address block has 19 fixed bits, so now there is 11 bits at host portion. The remaining 2 bits can be set with the minimum value. Here we set 0, 0. Okay, 0, 0, 0, 0. So the prefix is notation with the CIDR for Cambridge University can be set the minimum with x equals 0. So 0, 0, 0, 0. So the base address is 194.24.0.0. Then slash how we can get 21. That means since the length of the host portion is 11, then 32 minus 11, then we get the length of the prefix is 21. Right? You can get the 21. So this is Cambridge University. This is Cambridge University /21. Then we assigned address for Edinburgh University. Do we understand? Edinburgh University is, we can use this equation 2x should larger than or equal to 1024. So x, we can set x equals 10. 10 means the length of the host portion is 10 bits. 10 bits. 8 plus 2. 10 bits. Then 10 bits, so the length of the prefix for Edinburgh University is 32 minus 10. It is 22, right? So 22, then the remain 3 bits undetermined. Then since this bits has used 00, so for Edinburgh University, these 2 bits must not same as the former one. So since this is 00, then for Edinburgh can use 01. So make sure it is different from the first. Then ensure there is no overlap between the 2 address block. Then the remain we can determine with the minimum value. We use 0. So this 3 bits is 010. Okay, then we can determine the base address is 194.24.8. Here is 00004 zeros, then followed with 1000. So when calculate the base address, we can set x equals 0. Do you understand? So we can get .8.0/22. Then we assign address for Oxford University. Oxford University needs 4,000. Then we, according to this inequation, 2x should be larger than or equal 4,000. 4096, right? So x equals 12. X can be set with 12. That means 12 can be 8 plus 4. So the length of the host portion for Oxford is 12x with host portion. Then the remain one bit here. 1 bit here, how to determine the value? Since the former address block have used 0 here, right? 00, then it must not same with the former one. So we can set with 1 bit here. So then since the host portion length is 12, then the length of the prefix is 32 minus 12. It is 20. It is 20. Then how to determine the base address? Then we can set x equals 0. X equals 0 means 0001, 000, 4 zeros. So here is 16.16.0/20, right? So we can assign the address block for these universities. The third line can be omitted. Okay, do you understand? It is a typical application in the in a comprehensive big questions, subnetting and CIDR. Okay, this address CIDR address block can be written with traditional address range from the minimum address to the maximum address. This is a range of IP address. They are same. So since this is a CIDR scams, so we can use the CIDR notation with a slash notation. Okay, do you understand? If you have any questions, you can send messages in the discussion area. So if you have any questions, you can send questions and told me. Okay, please illustrate again. If you have any questions, you can send a message in the discussion area. Now, if you have no questions, I will continue with the next chapter. Okay, with the next chapter. Okay, we review this because network layer is very important. Is very important of the whole textbook. So, and it is the kernel of the whole network architecture. Some questions I have listed many questions. Okay, next I will turn to the next chapter. Transport layer, we will study these knowledge points: transport service, elements, congestion control, flow control, and some typical protocols at transport layer, UDP and TCP. UDP means user datagram protocol. TCP means transmission control protocol. Then we will discuss some performance issues and the new development of transmission protocol such as DTN, delay tolerant networking. Now we should introduce some concept of transport layers. We know the network there provides end-to-end packet delivery, actually machine-to-machine, right? Provides machine-to-machine packet delivery using datagrams or virtual circuit. Now, transport layer based on the network there to provide data transport from a process on the source machine to a process on the destination machine. So if network layer provides machine-to-machine transport, then transport layer provides services, provide network transport from a process on the source machine to another process to a process on the destination machines with a desired level of reliability that is independent of physical networks currently in use. It provides the abstractions that application need to use the network. Okay, network transport layer. Transport layer is very important for providing the transport services for users. Without the transport layer, the whole concept of layered protocol would make little sense. Okay, without the transport layer, the whole concept of layered protocol would make little sense. So transport layer is very important to provide abstractions the applications need. So in this chapter, we will study the transport layer in detail, including its services and choice of ARP design to tackle issues of reliability, connections, and congestion control, protocols such as TCP and UDP, and their performance. In the following sections, we will provide introduction to the transport service. Then, what kind of services does the transport layer provide? Then, we know in the network there are two kinds of services, connection-oriented. The other one is connectionless services. Then we will examine two sets of transport layer primitives and transport services. The ultimate goal of transport layer is to provide efficient, reliable, and cost-effective data transmission service to its users, normally processes in the application layer. Okay, to achieve this goal, the transport layer makes use of the services provided by the network there, then provide services for the application layer. So then the software or hardware within the transport layer. Then the transport layer has some software component or hardware component to provide the services, right? Then the software or hardware within transport layer that does the work is called transport entity. So the transport entity can be located in the OS kernel, operating system kernel, in the library package bound into network applications in the separate user process or even on the network interface card. The first two options are the most common. So generally, then the transport entity locates in the operating system kernel or in the library package bound into network applications. So this is the widely common. Then in the following section, we will provide in the transport services in detail. Now, services provided to the upper layers. Here we know the network there. So transport layer has transport entity. Transport layer or entity uses the services from network there and provide the services for application there, right? Then the places between transport layer and application there is the interface, that called transport service access point. That is the interface between application and transport layer. The unit of transport layer is called segment or datagram. For TCP, it's called segment. For UDP, it's called datagram. So this figure 1 illustrates the network, transport, and application layers the relationship between the three layers in the network architecture. Services provided to the upper layers includes two types of transport services. That includes connection-oriented transport service and connectionless transport service. So connectionless services and connection-oriented transport services. So two kinds. Connection-oriented transport service is similar to the connection-oriented network service in many ways. In both cases, connections have three phases. That is, establishment of the connection, the data transfer through this connection. Then, when finished transmission, then the connection will be released. So it includes three phases: establishment, data transfer, and release connection. The addressing and the flow control are also similar in both layers. Furthermore, the other kinds of transport service is connectionless. Connectionless is also very similar to the connectionless services in network layer. Now, the obvious question is, since the services connection-oriented transport services is similar to the network services, the connectionless transport service is very similar to the connectionless network services. Well, since they are similar to each other, why we need transport service? Why we need transport layer services, since they are similar to each other? Then why are there two distinct layers? Why is one layer not adequate? Why is the answer is subtle but crucial. The transport code, the reason is because the transport code runs entirely on the user's machine. The transport code runs entirely on the user's machine, but the network there mostly runs on the routers, which are operated by the carrier, operated by the ISP, Internet Service Provider, at least for a wide area network or Internet. So the routers, the network layer mostly runs on routers, which are operated by ISP, Internet Provider. Now, so users cannot control the devices in the network, right? So what happens if the network layer offers inadequate service? What happens if it frequently loses packets? So since the network layer operated by the carrier, the operator, then what happens if network layer offers inadequate service, frequently loses packets? What happens if routers crash? If routers crash from time to time, how can the users do? How can the users do? How can the services, how can users can get get reliable information transfer. So the users have no real control over the network there. So they cannot solve the problem of poor services by using better routers or putting more error handling in the data link layer, because they don't own the routers. The routers belong to the ISP, not users. So the users have no real control over the network there. The user cannot select the better routers to pass. The routing is determined by the ISP. So the only output on the top of the network there, another layer that improves the QoS for the users, right? The only possibility is to put another layer over network there to improve quality of service for users. If in the connectionless network, packets are lost or mangled, the transport entity can detect the problem and compensate for it by using error detection and transmission, or FEC, right? So users need another layer over network there to improve the quality of service when the network cannot provide reliable transfer. In a sense, the existence of transport layer makes it possible for the transport service to be more reliable than the underlying network. Furthermore, the transport primitives can be implemented as calls to library procedures to make them independent of network primitives. Network service calls may vary considerably from one network to another. For example, it's different between the wired network or wireless network. So hiding the network service behind a set of transport service primitives ensures that changing the network merely requires placing one set of library procedures with another one that does the same thing with a different underlying service. So this is the advantage of the layered network architecture, right? So to allow users to access the transport service, the transport layer must provide some operations to application programs. That is a transport service interface. Each transport service has its own interface. So in this section, we will first examine a simple transport service. A simple transport service through some reasonable assumption to simplify the questions. Okay, so hypothetical means we have some assumptions on the transport services and its interface to see the bare essentials in the following sections. Okay, then we look at a real example. So as the beginning, we look at a simpler transport services. Basically, the transport services is different from the network services, although they are similar to each other. The main difference is that the network service is intended to model the service offered by real network. The network service is intended to model the service offered by real networks. We know real networks often lose packets, right? Real networks without assumption. That means network cannot be ideal environment. So they always lose packets. So the network service is generally unreliable, lose packets from time to time, generally unreliable. The connection-oriented transport service, in contrast, is reliable. Of course, real networks are not error-free, but that is precisely the purpose of the transport. So the goal of the transport layer is to deal with the not error-free problem. So the transport layer is used to provide a reliable service on the top of an unreliable network. That is the point, right? That is the point of the transport layer. It is used to provide a reliable service on top of an unreliable network. So this is the point we should understand very well. The second difference between network service and the transport service is whom the services are intended for. Whom are intended for. The network service is used only by the transport entities. Fewer users write their own transport entities, and thus fewer users or programs ever see the bare network services. The bare network services. So network services and transport services is whom the difference is whom the services are intended for. We know network services is intended for transport layer. The transport services is intended for the application layer. So fewer users write their transport entities based on bare network services interface. So in contrast, many programs see the transport primitives directly. Consequently, transport service must be convenient and easy to use. Right? So in the experiment 4, in the last experiment, we can use some transport primitives to program, to code a pair of networking programs, a client and a server programs for the last experiment. Okay, next, okay, so much for today. Notice that on this Friday, we will have the third experiment to install and configure network servers. Typically, we can test information server, IIS or Apache on Ubuntu or Unix, and design a cool homepage for yourself. Design a cool homepage for yourself. Okay, so much for today. Thank you. Bye.